So distributed sources. This is a difference in approach from the discrete source modeling. So far we've always looked at dipoles and regional sources in the discrete modeling, and now we want to look at distributed modeling. So we want to look at minimum norm, S, LORETA, LAURA, CLARA, etc. So what's the difference? In distributed source modeling, we subdivide the brain into a grid, a regular grid, and we put a source on each node of this grid. So we no longer work with 2 or 3 sources, we work with hundreds and thousands of different sources. And each of these sources can be active or silent, but in principle the source is always there. And this makes a few radical changes in the mathematics of computing these solutions. If we look at the old case that we had so far, we worked with the overdetermined problem, where we had many fewer sources and channels. So if you look at the data matrix here in orange, we've got n channels and t time samples, and it's quite a large matrix compared to the matrix for the source waveforms, where we, for example, here only have 3 different sources. And so in this case, we will always get a solution for this equation because we have many more observations than unknowns. We only need to reconstruct 3 source waveforms. And the good thing about this is that we get a good data reduction, we get separation of different brain activities, but as we've already seen, it requires a user decision on not just the number of sources, also on the fitting interval, and so on. So it's a bit complicated. Distributed sources, we have the other situation. Now we have many more sources and channels. So now we have a large source waveform matrix. So at each part in the brain we can have a source, and they're all entered into this mathematical formulation, and we just calculate how active are these sources at any given time. Yeah, so this is the underdetermined problem, and the good thing is it's an automatic process, so we don't need to put much prior knowledge or hypothesis into this. A bad thing is we need to apply an additional constraint to even get a solution for this equation, because now we have many more unknowns than observations. We need to apply additional constraints. These are usually what we call the regularization, and in this case we get no longer a good separation of brain activities. So even if we have a very focal activity that's only in one place in the brain, it gets smeared out into a large patch of activity in our distributed solution. So you can never get the perfect world, there's always some drawback. So there's some additional assumptions that are made. We need the constraints to get to the solution, as I already said, and this is because there's various different things you can do. There's a complete zoo of methods available for these distributed solutions. For example, the minimum norm is maybe the most popular or well-known method. It's the solution with the smallest overall power, and it can also additionally get a depth weighting. Then we have the LORETA, also a very popular method. This is the solution that's called the smoothest across source space, and it can also apply depth weighting to give more weight to deep sources, which otherwise would be sort of at a disadvantage compared to more surface-oriented sources. Then we have the S-LORETA, which is based on an unweighted minimum norm image. The LAURA is another method that's based on minimum norm and has an autoregressive function. Then we have 2 methods, which I'm going to talk about a bit more in the future. They're called CLARA and SS-SLOFO, and these methods, they are iterative methods. So they start with one of the other methods, and then they iteratively reduce the source space to get to a more focal solution. So what they try to do is to combine the advantages of the distributed and the discrete modeling by first working on a distributed automatic method and then gradually getting more focal and bringing out the actual patches of brain activity that really had the activity. So we're going to look at these now quickly to see which ones are good and which ones are maybe not so good. And yeah, no surprises. I'm going to work again with the auditory example because we already know what we roughly should expect here. I'm going to work with the grand average, the low condition, and use that for our distributed source example. Let's go with the low condition and use the same parameters as we had before. And for comparison, we're going to load a solution that we obtained for dipoles, the two regional source solution for the low condition in the auditory cortex. And now, how do we get to a distributed solution? Well, we have two options. One is available from the menu up here. It's called Image. Then you go to Volume Image, and then we can select the different methods. And we're going to start with the LORETA method. And this automatically will choose the spot of maximum intensity. Yes, and then show us the result. So it's automatically set the cursor at the maximum of 96 milliseconds, where we expect the N100, and we can then look at this result also by enlarging these heads, and we can see that it found 3 different maxima. It says that in the title bar, and automatically it slices the brain at the highest maximum, which is in the left. This is a radiological view here. So in the left hemisphere, not so far away from the position where we expected the auditory source. Go to the next maximum. This is actually in the right hemisphere and also not too far away, but still some distance away from the auditory source. And the third maximum is in the cerebellum, and this is some phenomenon that we often see in distributed modeling, that we get some activation in the cerebellum because the cerebellum is very far inside the brain, and it's a good thing to explain noise in the data. So these sources are also sometimes called ghost sources because they're not necessarily real sources. They may be just artifacts. But the LoRa method at least showed us 2 maxima, and they're not too far away from what we expect. So next method is the LORETA, and for simplicity we can also use this button here in the center, this arrow button. This will give us all the methods for distributed imaging that are available. So let me just go down to LORETA, select that, and then look at the result here. And this only shows us 1 large maximum here in the center. So this is a very smooth method, as it says. It gives us the solution with the least change in intensity by neighboring voxels in the brain, and the disadvantage is that it just smoothes a bit too much in this case and just finds 1 maximum in the center. So S-LORETA is a similar result. It's got 2 maxima, 1 in the center, 1 very far out and very little intensity. So also really just 1 large maximum. SW-LORETA is the LORETA with depth, S-LORETA with depth weighting, has a similar result again. So let's move to the iterative methods. We've got the SS-SLOFO, which is based on the S-LORETA, and that gives us 2 maxima. So 1 again in the right hemisphere, second one in the left hemisphere. The left hemisphere one is really close to our auditory source. The right one is a bit further away, but also in the right ballpark, you could say. So, and the last method I want to mention is the CLARA. This is our own in-house method. There's just been a publication again using Clara for epilepsy analysis, and the Clara comes up with 3 maxima. So one is close to the right hemispheric source, second one is very close to the left hemispheric source, and the third one is again the ghost source in the cerebellum. So this first run through the methods could set, at least for this bilateral activation in the auditory cortex, the iterative methods worked better, and the LoRa was the only other method that showed 2 distinct maxima in the 2 hemispheres. A few things that can be adjusted by these methods are parameters. So if I click this arrow button again for the settings, I can then change some dials. For a start, I can change the voxel size in the brain that is used. The smaller the voxel size, the longer it will take to compute. And then there's various parameters I can change, so it's very flexible, and this will take much too far if I start explaining all this. So when you play around with BESA, please be aware that this option exists. You can change all these parameters for the distributed methods, and there's a help function available to explain all these different settings. Yeah, so since we don't have much time left, in fact hardly any, before the coffee break, I would like to have a very brief talk about our surface-based methods. So let me explain what this is. The difference between the volume methods and the surface-based methods. Well, the volume methods, they work on a regular grid, and we don't have any constraints on the source space. We can just work anywhere within the brain. Now, if we look at the surface, we can also reconstruct the brain surface and just constrain the sources to be on that mesh that we constructed for the surface. So physiologically, that should make sense because we expect this activation to be on the cortical surface. In any case, these are both underdetermined problems, and we need some additional regularization to get to a solution. So again, looking at the differences in the grid that we're looking at, on the left-hand side, we can see the schematic of the grid that's used for the volume methods. So each grid node, for example, this red node here, will have 6 nearest neighbors, 4 in its own layer and 2 in the upper and lower layer. And so we always have a good definition of a neighborhood, and the neighborhood is equidistant over the whole grid. On the other hand, on the surface, we have a neighborhood that depends on the mesh. So if you look at this red node here, we can see this one's got 1, 2, 3, 4, 5 nearest neighbors in this triangulation. But if you look at this node, for example, this node here, this has 1, 2, 3, 4, 5, 6, 7, 8 nearest neighbors. So even in one mesh, there can be a lot of difference in the neighborhood relationships between all these different nodes. And this is a little bit of a problem for the LORETA method because that uses a spatial weighting that relies on the Laplacian operator. So I had to go and find a good representation of this Laplacian on the surface that can work with all these different meshes. And that was the main issue with our surface imaging methods, and we think we solved it. So if you look at the solution, we've come up with a few different Laplacians that we can apply to get to our LORETA and Clara solutions on the surface. So one of them is the graph Laplacian, which is simply a neighborhood estimator that looks at each neighbor with the same weight. But we also have different Laplacians, for example, the geometric Laplacian with area weights, where each neighbor gets weighted with the shape of its triangle and also the size of the triangle that it comprises. So these can all be used. By default, we use the graph Laplacian because it's the most robust. Before we go to the break, I'm just going to run through these examples with our different methods. We need to go to a dataset where we have a co-registration, because otherwise we will not see a nice brain image. So let me go back to a dataset from the set of this is a dataset from the auditory intensity. It's just one subject that was co-registered. So let me check. Yeah, we have a co-registration here, and we can use this dataset for our estimation. So same filter settings. On this set of methods, we can now also use these surface-based methods, and we can start with the minimum norm surface method. We need some preparation of the cortical mapping, and one thing that takes a little bit of time is to compute the interpolation on the surface from the calculation mesh to the display mesh. So that takes about 20 to 30 seconds to compute. And should be finished very shortly, and then we can see the results for the minimum norm image. What we would expect is that we get a bilateral activation. So here's the result, and let me make that larger. So this is the L2 minimum norm, and we can see a weak and widespread activation on the left cortical hemisphere, and a more focal one on the right hemisphere, but this is more posterior than we would expect, where we would expect the Heschel gyrus to be activated. So this is the minimum norm. We can now switch over to the cortical LORETA. So again, this is the LORETA, which means a smooth solution, but calculated on the cortex. And this is the result. So here we get a better positioning of the maximum, so we actually get close to the cortical activation that we expect, the Heschel gyrus on both hemispheres, and we can see a wide spread of activation. One thing we would like to achieve is to get a more focal, and this is where the cortical Clara comes into place. Again, our in-house method. Cortical Clara is the iterative application of LORETA, and after each step we get a reduction of the source space to get a more focal solution. And we also await the next image with the results of the previous image, and the result here is different. I need to scale it up a bit. And I can now see that I really get a very focal solution, and it's so far inside that it's hard to spot sometimes. You can see it's just a bit above the Heschel gyrus in the left hemisphere, and the right hemisphere it really activates the Heschel gyrus, so I get a very nice result. And remember, this is only the spherical head model, so if I had a FEM model for this, it would get even more precise probably. And I can also now check on the local maxima, so I can jump to the first local maximum and highlight this maximum. Let me see where it is. Yeah, it's just in here, so I can see this little white sphere. I can jump to the next maximum, and this should be the other hemisphere indeed. And I can also see the dipole from there, so I can also use these results to generate dipole solutions from the distributed solution results. And if I can't see the source because it's too far inside, I can also use the inflation of the brain. So this will blow up the brain to a smooth surface and still show us the cortical folding by a gray value, and show us the activation on top of that. So again, this takes so half a minute or so to prepare the mesh geometry. And while this prepares, I'll tell you as well that and this is a new feature in the BESA Research 6.1, this cortical imaging. And another new feature was that we implemented the so-called age-appropriate template models. So we've got some head models for children that are very useful for example, epilepsy analysis in young patients, which are also available with BESA Research 6.1. But we don't have time to explore this much further. Yeah, okay, this is the result for the cortical clara on the inflated brain, right and left hemisphere. And we can see the right hemisphere is almost perfect. The left one is a bit too high, but overall a very good result for a distributed method. Okay, this was enough talking from my side. So if there's other questions, otherwise we can have a short break. Okay, the cortical source imaging is very well suited to problems where we have sources close to the cortex, for example, somatosensory, auditory, or visual stimuli. It is maybe not ideal for situations with very deep sources. So if you look at rhythms, for example, so default mode network or something like this, maybe then it's better to use a volume-based imaging, because then you need more emphasis on deeper sources that are maybe not so well imaged in the cortical surface. But I think our experience with the cortical surface is very good so far. We have very good results for all the experiments that we have in our examples, and we recommend it. We also think we should try several methods, so you can be sure or more sure of your results if you have a convergence between different methods. So if you look at the cortical clara here and compare to the clara that's done in the volume, if they give you similar results, then this is a very good indicator that you have that you found a good solution. And if you get a high discrepancy, then maybe you need to start thinking, is there something else in the data that I haven't taken account of? Yeah, so I did not show you the automatic segmentation in BESA MRI. So one step that happens is that in BESA MRI, before I can co-register, I need to segment this. So I need to go through a segmentation workflow. First, you need to set some landmarks for the Thaler-Rath transformation, and then there's an inhomogeneity correction and an automated scalp and cortex segmentation and inflation that takes place. So these steps take about 25 minutes altogether for each data set, and this is something that I've already prepared before this talk. So what you can do is, if you have several MRIs, you can do the user interaction part for each of them, and then put them in a batch to run overnight to finish this automated segmentation. If you do a co-registration with an individual MRI, then you can display the results in the individual anatomy. And then the second step is to not just do a co-registration, but also use an individual head model. So these are two different things. We can do a co-registration, but we can still use a four-shell ellipsoidal model. We just have a more accurate representation of the source space in the individual MRI. And then we can also go the next step and perform an individual head model, which then gives us a better modeling of the currents in the brain. So should again give us a better localization. This is just working with a spherical shell model, but with the co-registration. And instead of using the co-registered brain, I could also use the standard MRI. So this would just show me the result in the average brain if I did not have a co-registration for this individual brain. Yeah, there's a different source space available. So in the volume image, we have the complete volume is available as a source space, and the sources can be anywhere in that volume. In the surface, we only we only allow the sources to be on the cortical surface. So they will not be in the deep brain structures, and so this will already reduce our source space and make it a bit easier to find a focal solution compared to the volume image. And also we don't need to worry so much about the depth weighting. So in the volume, sources that are deep sometimes have less influence on the image than sources that are close to the surface. There's always an issue with deeper sources in the volume, and with the cortical surface that issue is not so strong because we already have a restriction in the source space. And yeah, it's just there's other things that are different. For example, for the LORETA, in the volume we have the grid, the regular grid. And in the surface, we have the surface-based two-dimensional Laplacian operator, and that again causes a slightly more focal result for the LORETA. I don't think I can say that one method always works better than the other. It's for some applications one method may work better, and for others another may work better. So it's always good to try at least one volume and one surface method, I think, and see if they give us similar similar results. I think if you want to do individual analysis, so for source localization, you should go for an individual head model if you can. If you want to do a group analysis, it may be simpler to use a standard head model, because then you have a standardized setup. So if you're looking at statistical differences between two groups, I think it's a good idea to use a standard head model and not an individual head model. But if you're looking at individual localization, then you should, if possible, use an individual head model.
Thank you.
Thank you.